Today's talk is not about any particular Go changes, but about the overall process of change, specifically how we decide which changes we make. The obvious first question is, why does Go need to change at all? Why can't we just be happy with Go and leave it alone? And the easy answer is that we don't always get things right the first time, like in this picture of the first plush gopher, compared to the final version that you all received at check-in. But there's a deeper answer, too. A former colleague of mine used an email signature for many years with a quote from the biologist and science fiction author Jack Cohen. In the quote, Cohen says, "There is this special biologist word we use for stable, and that word is dead. Everything that is alive changes, adapting to new surroundings, repairing injuries, and so on. And programming environments require change, too. Unless we want Go to die, it needs to adapt to new surroundings, like new protocols, new operating systems, new important use cases. And we need to fix bugs we discover, along with language, library, and ecosystem problems that become apparent only over time or only once Go has reached a certain age or size. Go has to change to improve and keep up. This talk is about how we decide which changes to make. So there are three parts to this talk. The first part is about what kinds of changes we want and don't want for Go. The second part is about how we use data to decide which changes to make. And the third part is about our plan to add opt-in telemetry to the Go toolchain to better understand how Go is being used and when it's misbehaving. By the end of the talk, you will understand the process for thinking about how we decide on changes for Go. You'll understand the importance of data for making those decisions. And I hope you will understand why opt-in telemetry is a good additional source of data and maybe even be willing to opt in when the system rolls out. So let's start with this. What kinds of changes do we want for Go? If we don't agree on this basic point, we can't agree on specific changes either. So here's an example. Should we add a Perl statement to Go that lets us write functions in Perl? I think we shouldn't, but he disagrees. And to resolve that, we need to understand why we disagree. So John Ousterhout wrote a wonderful document titled Open Decision Making, and it was about his experience running startups, but it applies almost exactly to open source projects as well. And one of the most important points he makes is this. If a collection of smart people all look at the same problem with the same information, and if they have the same goals, then they're likely to reach the same conclusion. So if you and I disagree about embedding Perl in Go, the root cause is almost certainly that we have different goals for Go. So we have to establish what Go's goals are. Go's goal is better software engineering, especially at scale. Nearly all of Go's distinctive design decisions are aimed at that goal. We've said this often, including these two articles, Rob's presentation from 2012 and our CACM article from last year. And again, Go's goal is better software engineering. Now, what about Perl's goal? 20 years ago, when I was younger and more naive and Go didn't exist yet, I wrote and deployed a significant distributed system in Perl, and I got away with it. And I love Perl for what it is, but it's not aiming at better software engineering. If we disagree on that, then maybe I should define what I mean by software engineering. I like to say that software engineering is what happens to programming when you add time and other programmers. Programming means getting a program working. You have a problem to solve, you write some code, you run it, you debug it, you get your answer, and you're done. And that's programming, and that's certainly difficult enough. But then what happens when we add time and other programmers? What happens when that code has to keep working day after day, even with other people working on it? Then you need to add tests. So make sure that the bugs you fix are not reintroduced later, not by you 6 months from now, and not by that new team member who just started and is unfamiliar with the code. This is why Go has provided built-in support for tests from day one, and why we established a culture of always adding tests with any new bug fix or code that we add. So what happens when the code has to keep working year after year, even as Go itself changes? Then we need to emphasize compatibility, which we did in Go 1. And then more recently, Go 121 shipped many compatibility improvements that I previewed here last year at GopherCon. What happens when you have a lot of code and it needs some kind of global cleanup? You need to write tools. And the inevitable first stumbling block is that these tools need to make changes that mimic the formatting of the code around them to avoid spurious diffs when they rewrite the files. GoFumped exists to enable those kinds of tools like Go imports and Go please, as well as the custom tools you might write yourself with the packages we provide. Speaking of which, when you use packages that other people provide, the first stumbling block is that multiple people might want to write packages with the same name like SQLite or YAML. How do we identify which one to use in a given program? Go's import paths are URLs to answer that question in a decentralized, unambiguous way. As time goes on, the next problem is picking which version of a specific package to use and deciding whether that version works with all your other dependencies. This is why we provide modules and workspaces and the Go module mirror and the checksum database. The next problem is that everyone's code has bugs, including security bugs. And you need to find out about the most important bugs so that you know to update to the fixed versions. This is why we added the Go vulnerability database and Go vuln check, which Julie Q will be talking about to close the conference tomorrow. Those are large examples, but there are also small ones like adding new protocols like HTTP3 or removing support for insecure platforms, fixing and deprecating error-prone APIs to avoid common mistakes, especially in large code bases. This takes us to the Go proposal process, which is how we make decisions about which changes are accepted and which are declined. When we think about those decisions, it turns out that using data is very important for reaching consensus. Very briefly, anyone can file a Go change proposal on Go's GitHub issue tracker, and then a discussion happens on that issue in public where we try to reach a consensus among the participants about whether to accept or decline the proposal, or how to change it so that it can be accepted. Over time, we've come to appreciate the importance of a second phrase in John Ousterhout's observation. Consensus is likely when the people looking at the problem have shared goals, but also shared information. In the very early days of Go, there were very few of us making decisions, and we based them on technical judgment and intuition informed by our past experiences. Those experiences were the information we were using, and we reached consensus most of the time because our past experiences overlapped enough. I think most small projects work that way. But as decisions scale to many people, there's not as much shared experience. We need a new source of shared information. And the best source we found is to gather actual data, and then make that data the shared information that we use. But where do we get that data? For Go, we have many potential sources, and each of them is suited to specific kinds of decisions. Let me show you a few of them. One source of data is talking to Go users, and we do this in a variety of ways. First, there's the Go user survey, which we've done every year since 2016. The survey is good for understanding the most popular uses of Go and the most common problems that people face. For many years, the most common problems, the top two, were the lack of dependency management and the lack of generics. And we use that information to prioritize developing Go modules and then generics. Another source of data is the surveys that we can run inside VS Code using the VS Code Go plugin. And these surveys help us understand how well VS Code Go experience works. The final source of data, direct from users, is research interviews and user experience studies that we conduct throughout the year. These let us start to identify patterns or get more information about specific topics from a small group. Surveys and interviews gather data by talking to users. Another data source is reading code. We can analyze the open source Go modules that have been published. For example, before we add a new Go vet check, we run it on the subset of the open source Go corpus and then read a random sample of the results to see whether the check is pointing out real problems and whether it has false positives. For Go 122, we're planning on adding a Go vet check for calls to append that append nothing at all. So here are two code snippets that were flagged by the check. The top one suggests that perhaps the developer believes that append makes a copy of the input slice, and the bottom one is not harmful, but certainly awkwardly phrased. Here are another two. In the top one, either the for loop doesn't run or it doesn't stop because e.sigs is not changing inside the loop. The bottom one also seems like a clear bug. The code goes out of its way to decide which list to append old message to, and then it doesn't append it to either one. So since all the flagged code snippets that we sampled were questionable or outright bugs, we decided to add the check. The data was much better than our intuition, which was that this wasn't that big a deal. All these approaches are working on a very small number of samples. For a typical code analysis, I like to read maybe 100 code snippets, which is a minuscule fraction of all the Go code in the world. And the last Go developer survey had just under 6,000 responses out of maybe 3 million Go developers in the world, so much less than 1% of them. A good question then is why these tiny fractions tell us anything about the larger populations they're drawn from. And the answer is that sampling accuracy only depends on the number of samples and not the overall population size. This seems counterintuitive at first, but suppose I have a giant box of 1 million gophers for a really large GopherCon to give out, and I pull 2 of them out at random. First I get 1 blue gopher, and then I get a pink gopher. And based on just these 2 samples, I estimate that the box is approximately half blue and half pink. Now, how surprised would you be if I told you that actually the box is equal parts blue, pink, and gray? You wouldn't be too surprised, because we just only pulled 2 gophers. If the box really is 1/3 blue, pink, and gray, then each of these 9 pairs is equally likely. And the chance of getting 1 not gray gopher is 2/3, and the chance of getting 2 is 2/3 squared, or 4/9. So not seeing a gray gopher is going to happen almost half the time. So it's not very surprising that there are gray gophers in the box and we didn't see them. On the other hand, suppose I pull 100 gophers out, and there are 48 blue gophers and 52 pink gophers. So again, I estimate the box is about half and half. Now, how surprised would you be if I told you that the box is equal parts pink, blue, and gray? You should be a lot more surprised. And in fact, you shouldn't believe me at all. Because if that was true, the chance of getting 100 not gray in a row is 2/3 to the power 100, which is around 10 to the minus 48. So random chance does not explain what we just saw. Either I'm lying about the box, or I'm not pulling them out randomly. So maybe all the gray gophers are at the bottom, and I'm not reaching in deep enough. Now notice that none of this depends on how many gophers are actually in the box. It only depends on how many we pull out. The math for the accuracy of the specific predictions we're making is more complex, but it has the same effect. Only the number of samples matters, not the number of gophers in the box or the population we're drawing from. Now, in general, the math is too difficult to calculate by hand. So here's a table you can find on my blog. It says that if you take 100 samples and estimate percentages based on those, then 90% of the time, the estimates you get will be within 8% of the true underlying percentages. And 99% of the time, they'll be within 13%. So they're reasonably good estimates. Not great, but okay. If you have 5,000 samples, like in the Go survey, 90% of the time, the estimate will be within 1%. And 99% of the time, it will be within 2%. Now, one caveat, an important one, is that the samples need to be random, or at least not correlated with what you're estimating. You can't only pull gophers from the top of the box. But if you avoid that mistake, then when you're trying to estimate whether a new API will be useful, or whether a particular vet check is worthwhile, or some other design decision in your system, it's reasonable to spend an hour or so examining 100 samples by hand. If it's a bad idea, that will become apparent very quickly. And if it looks like a good idea, then spending another couple hours checking more samples, either by hand or with a program, will improve your estimates considerably. And it's a very small cost compared to the cost of making a bad decision. In short, the magic of sampling is that sampling turns many one-off estimations into jobs that are feasible to do by hand or with small amounts of data. This is why all the data sources we've seen already managed to represent the entire Go developer population reasonably well. That brings us to the third part of the talk, telemetry in the Go toolchain. Telemetry is also going to be a small sample of Go developer usage, but it should be a representative one, and it answers different questions than surveys and code analysis do. Now, telemetry is always a contentious topic, especially for open source projects, so let me start with the most important detail. Uploading telemetry reports is entirely voluntary and opt-in. No data will be uploaded without you running an explicit command or using a dialog to opt in to the data collection. This is also not the kind of telemetry system that uploads detailed traces of everything you do. After I've described the system in more detail, I hope you'll find that you would be comfortable opting into this system. And in fact, the primary design constraint we gave ourselves was to make something that we would be willing to opt into if someone else were running it. Also, the system's not running yet, so you can't opt in today, but hopefully soon. Before we get into the details, the motivation for telemetry is that it provides different information than surveys and code analysis do. And the main two categories it provides are usage information and breakage information. Now, surveys let us ask broad questions about Go usage, but they're not great for detailed usage information. That would be too many questions, and it's a waste of time for respondents to answer no to 90 or 99% of them. This slide shows a list of things that we've removed from Go after warnings in earlier release notes. The last item on the list, build mode equals shared, is something we tried to remove, but after pre-announcing the removal, a few people objected and we left it in. Even so, it basically doesn't work with Go modules, so it seems unlikely that there's very much usage at all, but we don't have data, so it just lingers in the code base. Telemetry could provide us with basic usage information so that we can make those kinds of decisions with data and not guesses. The other important category is breakage information. If the Go toolchain is obviously broken, then we expect to get bug reports on GitHub. But it can be broken in subtle ways that users don't notice. One example is that Go 1.14 through Go 1.19 on macOS for 3 years accidentally shipped with standard library package binaries that had been pre-built with non-default compile flags. And that made them look out of date, so that the first time you ran the Go command, it recompiled the standard library, which meant that if your program imported net, which uses CGO, you needed a C compiler from Xcode to build the program. Now, we intend that when you download Go, you can build a Go program that just uses the standard library with no other toolchains at all. So requiring Xcode was a bug. But we didn't notice. Users got this pop-up. No one reported it on GitHub. And anyone who ran into this apparently just said, OK, I'll install Xcode, and then moved on with their day. And that's fine. They got their work done, but that's not the experience that we want. And so telemetry can provide basic performance metrics like standard library cache hit rate, so that the Go toolchain developers can notice a problem like this even when users don't. Another example is internal compiler crashes. The Go compiler doesn't stop at the first error in your program. It keeps going, trying to find different errors so you can fix them all and then recompile. But sometimes, continuing to analyze a program with known errors causes unexpected panics inside the compiler. And we don't want to show users a crash like this, where there's one error and then a crash. Instead, the compiler recovers from that panic and only reports the errors that it's found so far. This way, a Go user can fix the errors, which will probably also fix the panic that they didn't see, and the user's work is not interrupted by a compiler crash. That's great for users, but as the Go toolchain developers, we still want to know about those panics and fix the bugs. And telemetry can make sure that we find out about these bugs even though users don't. So to gather usage and breakage information, the Go telemetry design records counters and crashes. A Go toolchain program like the Go command or the Go compiler or Go please can define named event counters and then increment the counters when they happen. And the events can also be counted separately by which stack was in the program at the time. And these counters are maintained in local on-disk files and incremented for a week at a time. Now on the slide, Go Please and the other tools are writing counters to the weekly files. Once a week, an uploader program in the Go toolchain will fetch an upload configuration which lists the specific event names being collected that week. That configuration is changed only after consensus is reached in a public telemetry-specific proposal process review. And the configuration is served as a module to protect the integrity of the download and to keep a public record of past configurations. The uploader program then uploads only the counters listed in the upload configuration. So on the slide, even though many programs were writing counters, the uploader is only sending the counters for Go Please, because that's all that's being collected. And inside that, only the few counters that are actually being collected, even though Go Please may have written many more. There are some statistics about which editors are being used and latency, and there's one crash with a stack trace. And the stack trace only has function names from inside the Go Please program. It doesn't have user data that was on the stack. And notice, in fact, there's no event traces, there's no user data at all. It's just counts, names that already appear in the upload configuration, and function names that are already part of the Go toolchain. So telemetry in open source can create an information imbalance between those who have access to the data and those who don't. And we want to avoid that. Remember Ousterhout's rule. To reach consensus, we need everyone to have the same information. Because the telemetry uploads don't contain any sensitive data, and they're collected with a clear opt-in consent, we can republish those reports in full so that anyone can do any analysis they want. And we'll also publish basic graphs that are the main analysis that we'll be using. Now, an obvious question is whether enough people will opt in to telemetry to make the data accurate enough to make decisions. And luckily, the magic of sampling helps here. There are about 3 million Go developers in the world, so when the system is ready and we ask people to enable telemetry, even a 0.1% opt-in rate would be 3,000 developers, which our chart says is under 3% error 99% of the time. And if 2/3% of Go developers opt in, that would be 20,000 samples, which is under 1% 90% of the time, 99% of the time. Beyond that, we don't really need any more samples. If we consistently get more reports, we can adjust the upload configuration to tell systems to randomly not upload any given week. For example, if it looks like there's about 200,000 systems uploading, we can set the upload configuration so that each system uploads with probability 10%, so we still only get about 20,000 reports a week. So this system should work very well, even though we expect opt-in rates to be low. And as the rates go up, Go will collect less telemetry from any given system. Now, of course, that makes each person who opts in that much more important to us. Go telemetry is not ready for any of you to opt in, but when it is, I hope you will. So finishing up, this is what I hope you've taken from the talk. First, Go needs to keep changing, especially as the computing world changes around it. Second, the goal for any of these changes is to make Go better for software engineering, especially at scale. Third, once we agree on the goal, the next most important part of achieving consensus is having shared data to base the decision on. We need to all have the same information. Fourth, Go toolchain telemetry is an important source of data to augment the existing survey and code analysis data that we already use. And finally, while this entire talk has been about data and proper statistics, the ideas and the hypotheses about potential changes that we're evaluating always start with stories and individual conversations. And we love hearing these stories and talking to all of you about how you use Go, about what's working and what's not working. And we'll be hanging out at the Google Cloud booth downstairs the whole conference, so please come talk to us at the booth. Thanks very much. Welcome to GopherCon. Welcome to San Diego. Have a great time.